Okay, so we are now in module 2. Believe it or not, we are in the 5th week of the course. So we've gone through a quarter of it already. Now we're gonna do another set of topics. This one is the DP900, if I am not mistaken. Let me jump to the class. I believe it's DP900, the data certificate. Yes, DP900, Azure Data Fundamentals. It only has 4 parts, so I'll be doing a part a week. And just like the last one, there is a skill submission at the end. Again, you are more than welcome to jump ahead of me. It is not a requirement that you go at the speed that I'm going. Feel free to jump ahead. And if you are able to get through that and do the skill submission, awesome. A few students did find some links where you can get trainings and get vouchers to get those tests for free, which I will always recommend. If you are able to get the actual test and also get it for free, that's a win-win. If you do sign up for it and you take and pass the test, you'll send me the links are in Discord. Send me proof that you passed the test, and then I'll give you an A for that entire module because you got the test. So there's no point in me keeping you to do the work for that test. And then you'll be able to move on straight to module 3 and knock that out ahead of everybody else, which again is perfectly fine. There's no repercussions for that in my courses. So this first part in a series of 1, 2, 3, 4, 5 is explore core data concepts. That's new. Doesn't want to load. All right, let me reopen that slide there. Since when does Google not load its own slide deck? Anywho, while that loads, it opens with the first question: what is data? A collection of facts such as numbers, descriptions, observations used in decision making. You can classify data as structured, semi-structured, or unstructured. Structured data is typically tabular data that's represented by rows and columns in a database. And here is the picture of just a simple database. Databases that hold tables in this form are called relational databases. It's a math thing. The mathematical term relation refers to organized set of data held as a table. So if you think of data set in an organized fashion as a table, there it is a relational database. Each row in the table has a set of columns, has the same set of columns. Here's just one example of 2 tables that you would see in something like Excel or in SQL. Semi-structured is information that doesn't reside in a relational database, but still has some structure to it. For example, JavaScript's object notation or JSON. There are other types of structured data like key value and graph databases. So depending on the type of data, whether it's structured, semi, or unstructured, data will be stored in different ways. Structured data you'll see in things like SQL, which already has a section to run in the cloud. You can use that to create and access any relational tables. You can provision other services to use it. You could use even things like blob storage for unstructured data like videos or audio files using the Azure Cosmos database. Once you have it provisioned, the service will need to be configured so that users can be given access to the data. And that could be read-only access, read-write, or owner. You should always define that in the first place. If data is sensitive or secret level, then you want to restrict access to a few select users. Next, we have transactional systems. These are the most often what people consider the primary function of a business computing. A transactional system records transactions. It could be financial, like moving money between accounts, or it could be part of retail, tracking payments of goods or services. These are often high volume, handling many millions of transactions in a single day. They can be performed by transactional systems through online transactional processing, or OLTP. In order to do this, the transactional system is divided into small pieces. For example, if you're using a relational system, each table involved in a transaction will only contain columns necessary to perform the task. An analytical system is designed to support OLTP, or the online transactional processing, designed for users who need to query data and gain a big picture of the information held in the database. Analytical systems are more concerned with capturing raw data and use it to generate insights in order to make business decisions, for example. They all typically perform the similar tasks of data ingestion, transformation, querying, and visualization. So things like data ingestion is capturing that raw data taken from either devices who are measuring things, point of sale devices, financial data, data from weather stations, getting information from a source. The data transformation or processing takes that raw data and puts it in a suitable form in order to be queried. After the data is ingested and transformed, it can be queried for analyzation, and visualization just makes that data be understandable in things that we can understand, like rows, columns, documents, bar charts, all kinds of graphs and other means, other visual means. So relational and non-relational data have their similarities and differences. Relational databases provide the most well-understood model for holding data, since like Excel, with tables, columns, and rows. Non-relational databases enable you to store data in a format more closely matching the original structure. For example, in a document database, you could store the details of each customer in a single document. Retrieving details of a customer, including the address, is a matter of reading a single document. If two customers cohabit and have the same address in a relational database, you would only need to store the address information once. Here is more of a non-relational, how things can be intertwined with each other. In a document database, the address would be duplicated in the documents. Duplication not only increases the storage required, but can also make maintenance more complex. Relational and non-relational databases are suited to different workloads. Like we said, the relational databases are primarily doing transaction processing. A transaction is a sequence of operations that are atomic. That means either all operations in the sequence must be completed successfully, or if something goes wrong, all operations run so far in the sequence must be undone. So for example, bank accounts fall under this. Each database transaction has a defined beginning point, followed by steps to modify the data within the database. At the end, the database either commits the changes to make them permanent or rolls them back to the starting point when the transaction can be tried again. Transactional databases adhere to the ACID, atomicity, consistency, isolation, durability properties to ensure that it remains consistent. So the first one, atomicity, guarantees that each transaction is treated as a single unit, which either succeeds completely or fails completely. Consistency ensures the transaction can only take the data in the database from one valid state to another. Isolation ensures the concurrent execution of transactions leaves the database in the same state that would have been obtained if the transactions were executed sequentially. And durability guarantees that once a transaction has been committed, it will remain committed even if there's a system failure or a power outage or a crash or anything else. Databases who do process transactions are inherently complex because they have to do those four things together and be able to roll back at a moment's notice. Distributed databases store information across different physical locations. So they'll need to be updated, consistently across time as they're being updated and used. Analytical workloads are typically read-only systems that store vast volumes of historical data or business metrics, like sales performance, inventory levels, and so on. They're used more for data analysis and decision making, things that fall under business information. Analytics can be based on a snapshot of the data or a series of snapshots. Decision makers usually don't require all the details of every transaction because they're looking at the bigger picture in order to make those decisions. Batch and streaming data are two different ways to take data and process it. In batch processing, newly arriving data elements are collected into a group. The whole group is then processed at a future time as a batch. So for example, you could process data at a scheduled time interval, like every hour, or when a trigger happens. The advantages are large volumes of data will be processed at a convenient time. For example, when the server isn't used as much. It can be scheduled to run at a time when things are idle. The disadvantage is the time delay between ingesting the data and getting results. And all the input data must be ready before a batch is processed. That means everything has to be checked for errors or any possible crashes, as anything that, any like minor errors could prevent the entire batch from running. Stream processing will process the data as it arrives. Data ingestion is inherently a streamed process. This will happen in real time without waiting for other data. So this is things like financial institutions, online gaming, real estate. It's ideal for anything that's time critical and requires an instant real-time response. Between the ways that the two handle data, other differences could be in things like data scope. Batch processing can process the entire data in the data set. So a stream will only have access to the most recent data received. Batch processing will handle large data sets where stream is intended for smaller individual records. Performance, batch processing will take a few hours where stream will happen immediately. And analysis, You will use batch processing for complex analysis and stream for simple and quick responses. Like I said, this module is very basic, but feel free to ask any questions along the way. I have all my chats up. Where are the links? Oh, I already answered that one. Right. All the links are on Discord. In the world of data, there are a couple of important roles. 3 key ones that are mentioned are the database, the engineer, and the analyst. The admin is responsible for the design, implementation, maintenance, and operational aspects of the database wherever it is, whether it's on the cloud or locally. They're responsible for the overall availability and consistent performance and optimization of the database. They're the ones who work with other stakeholders to implement policies, tools, and processes for backup and recovery, along with security, like granting permissions to users as appropriate. The engineer collaborates with stakeholders to design and implement data-related assets that include ingestion pipelines, cleansing, transformational activities, data stores, and workloads. They are also responsible for ensuring data privacy. They own the management and monitoring of data stores and data pipelines. The analyst enables businesses to maximize the value of their data assets. They're the ones who build and design the scalable models, the cleaning and transforming data, and enabling advanced analytics and analytics capabilities through reports and visualization. So one creates the infrastructure, one manages the infrastructure, and one will take the data and turn it in whatever form is necessary. Your database admin has quite a list of tasks, like installing, upgrading database, allocating system storage, a lot of things that are considered IT, like monitoring, optimizing, backing up, maintaining archive data. A tool that you can use in Azure is the Data Studio, giving you a GUI that can connect with on-premise SQL Server databases, along with the Azure SQL database, Postgres, Data Warehouse, SQL Server big data clusters, among others. You can download and install extensions from third-party developers and use wizards within it. There is also the SQL Server Management Studio that also gives you a GUI to query data, perform administration tasks, generate scripts, and that sort. Within it, you can generate transact SQL scripts for almost all the capabilities that are provided. So you can schedule and automate a number of tasks. You can also, not surprising, use the Azure portal to manage SQL databases. A data engineer has these responsibilities on their hands. Data engineers should be familiar with a range of tools to create well-designed databases optimized for the business. They should have a thorough understanding of the architecture of the database management system, the platform on which the system runs, and the business requirements. For relational databases, they should be the most fluent in things like SQL. They should be able to use it to make whatever is necessary. Being able to use the command line to interact with them. The engineer is definitely the one who has to have the most profound knowledge. For example, SQL, if they're using relational databases. The analyst should be able to create all kinds of fun stuff like this, being able to take the data that the engineer has put together and being able to put it in a way that visually makes sense. So the administrator creates the VM or the service that the engineer will use to create the database within and be able to ingest data and do stuff with it. And the analyst will take that and make it and turn it into a way that is easy to read for example, the C-suites and managers. Moving about halfway across into the relational data. As we have already said, the realm of relational data is all tables, things that are organized in rows and columns. That is a relational database. They're all tabular. Entities are modeled as tables. Each instance of an entity is a row in the table. Each property is defined as a column. All rows in the same table have the same set of columns. A table can contain any number of rows. A primary key uniquely identifies each row in a table. No two rows can share the same primary key. A foreign key references rows in another related table. For each value in the foreign key column, there should be a row with the same value in the corresponding primary key column in the other table. Most relational databases support structured query language, or SQL. SQL can be used to create tables, insert, update, delete, all that kind of stuff. Thought I had some pictures of it, yeah, that's usually the way that you use relational tables. Aha. In these tables, you have an index. It'll help you search for data in a table. Think of an index over a table like an index at the back of a book. It'll have, your regular index contains a sorted set of references with the pages on which each reference occurs. So when you want to find an item in a book, you just look through the index. In the same way, you specify a column from the table, and the index contains a copy of this data in a sorted order with pointers to the corresponding rows in the table. When the user runs a query that specifies this column in the where clause, the database management system can use this index to fetch the data more quickly than if it had to scan through the entire table row by row, making the search faster. You can create many indexes on a table to be able to search for all kinds of stuff. Make things more specific. A view is a virtual table based on the results of a query. In the simplest case, you can think of view as a window on specified rows in an underlying table. For example, something like this would create a view on the orders table that lists the orders for a specified product. In this case, the product is P1. You can query the view and filter the data in much the same way as a table. For example, this query finds the orders for customer C1 using the view. So the query will only return orders for product P1 made by that customer, C1. A view can also join tables together using that join command. If you regularly need to find details of a customer and the products that they've ordered, you could create a view based on the join query together. This one finds the customer name and product names of all orders placed by the customer C2 using the view. From our point of view, we're more database admins than engineers and analysts, although we should be familiar with how to set those up, especially if we're the ones who are bringing a business into Azure. We should be able to help the database admin get started, or sorry, the database engineer and analyst get started and then let them take off. For us, it's all about finding what is the right platform to launch. Is it better to do it locally? Maybe the data that we're running has to be local to meet compliance or having backups, or maybe it is super confidential, or we could run it as a platform as a service, or run it infrastructure as a service. Whatever will meet best the need of the business. Now, while I did go kind of quick on SQL, I will say if you've never messed with SQL before, SQLbolt.com is a great resource to get hands-on learning SQL in a very easy to read and understand fashion. You don't have to install anything ahead of time. It is all in the browser. So you can learn SQL through your browser without having to do anything extra. If you've never worked with SQL, I highly recommend that site. Non-relational data allows you to store data in a flexible manner. There is no schema like there was in relational data where everything has to fit in a table and everything has to fit in the columns and the rows. It's all more loosey-goosey. Non-relational databases focus on the data itself rather than how to structure it. It means that you can store information in a natural format that mirrors the way in which you would consume, query, and use it. In a non-relational system, you store the information for entities, in collections or containers, rather than relational tables. Two entities in the same collection can have different sets of fields, rather than a regular set of columns found in relational tables. The lack of a fixed schema means that each entity must be self-describing. Often this is achieved by labeling each field with the name of the data that it represents. Something like this. Adding a new customer is a matter of inserting an entity with its fields labeled in a meaningful way. An application that queries this data must be prepared to parse the information in the entity that it retrieves. The way that it does it will vary. Each entity should have a unique key value. The entities in a collection are usually stored in a key value order. So here you can kind of see where those are. ID1, ID2. That is the simplest way to handle data in this form. So filtering data on other fields would require scanning the entire collection of entities, parsing each entity in turn, and then applying any query criteria to each entity to find any matches. So that might actually run a little slower than a relational. More advanced non-relational systems support indexing in a similar manner as the relationals. Queries can then use the index to identify and fetch data based on non-key fields. The Azure Cosmos database supports indexing even when the structure of the index data can vary from record to record. These non-relational databases can be used in things like IoT, retail and marketing, gaming, and web and mobile applications. Since they can restructure data into since they can handle various types of data and put them in a place for later searching. The types of non-relational data can be things like semi-structured. These contain fields, but they don't have to be the same in every entity. It's more of a per entity basis that you can find in a JSON file. There's a couple other formats, like Avro is a row-based format created by Apache. There's ORC, the optimized row columnar format that organizes data into columns rather than rows. And Paraquet, created by Cloudera and Twitter, contains row groups. So non-relational can handle the semi-structured, like these guys, and also the unstructured, data that doesn't contain or naturally contain any fields. These can be like video, audio, or other media streams, since each item is an amorphous blob of binary data. You can't really search. JSON is non-relational, whereas a table is relational. Non-relational data is an all-encompassing term meaning anything not structured as a set of tables, like JSON. Many different types of non-structured data exist. For example, a NoSQL is a rather loose term that just simply means non-relational. NoSQL databases generally fall into 4 categories: the key values, the document databases, the column family databases, and graph. The key value is the simplest and often the quickest type of NoSQL database for inserting and querying data. Each data item in a key value has 2 elements, a key and a value. The key uniquely identifies the item, and the value holds the data. The value is opaque to the database management system, and items are stored in key order. Write operations are restricted to inserts and deletes. If you need to update an item, you must retrieve it, modify it in memory, and then write it back to database, overwriting the original. The focus of key value is to read and write data very quickly. Search is secondary. The Azure table storage is an example of this. Cosmos DB can use it with Table API. The second form is a document database, representing the opposite end of NoSQL spectrum from a key value store. Each document has a unique ID, but the fields in the documents are transparent to the database management system. Document databases typically store data in JSON, or they could be things like SML, XML, YAML, JSON, BSON. Documents could even be stored as plain text. Typically, a document contains the entire data for an entry. All the items that constitute an entity are application specific. For example, an entity could contain the details of a customer, an order, or a combination of both. Document store does not require that all documents have the same structure, allowing great flexibility. Applications can retrieve documents by using the document key. Some of these databases can do in-place updates. Others do read and write as separate entities. They aren't optimal. They can ingest large volumes more rapidly, but they're not optimal as key value storage. The column family database organizes data into rows and columns. In the simplest forms, a column family database can appear very similar to relational conceptually. The real power of these guys is in the denormalized approach to structuring parsed data. For example, if you need to store information about customers and their addresses in a relational database, you might design a schema similar to the one shown below, or shown here. The diagram shows some sample data. Customer 1 and 3 have the same address. So the schema will ensure that this address information is not duplicated. The relational model supports a very generalized approach to implementing this type, but to find the address of any given customer, an application needs to run a query that joins the two tables. If this is the most common query performed, then the overhead associated with performing this join operation can quickly become significant if there are a large number of requests and the table themselves are large. So a column family database can handle this. They hold tabular data comprising of rows and columns, but you can divide them into groups known as column families. Each column family holds a set of columns that are logically related together. So the illustration is conceptual rather than physical, and is intended to show the logical structure of the data rather than how it might be physically organized. Each row in a column family database contains a key, and you can fetch the data for a row by using the key. The last set of the NoSQL is a graph database, enabling you to store entities, but the main focus is the entities, what they have relationship with each other. The graph database stores two types of information: the nodes that you can think of as instances of entities, and edges, which specify the relationships between the nodes. Nodes and edges can have both properties that provide information about that node or edge, like a column or a table. Edges can have a direction indicating the nature of the relationship. The purpose of this database is to enable an application to efficiently perform queries that traverse the network of nodes and edges and to analyze relationships between the entities. Now, with something like this, it's easy to ask a query like find all employees who directly or indirectly work for Sarah, or who works in the same department as John, that kind of stuff. And on to the last section, some data analytics. This is all about taking data and finding meaningful information and inferences from it. Could be things like organizational procedures and establishing a picture as to how the organization is performing or how to maintain business performance. Data can come from many sources. Could be historical data, could be fresh data, customer purchases, bank transactions, come from anywhere. Building the data warehouse requires that you can capture data that you need and wrangle it into an appropriate format. You can then use analysis tools and visualization to examine it, identify trends and causes. Data ingestion, like we said, is the process of obtaining and importing data for immediate use. Data processing will occur after ingesting the data and process it in a way that will be useful. That could be by using things like automated scripts, like Databricks, functions, cognitive service, and so on and so forth, in order to take that raw data and being able to put it where we can use it, like in JSON files or data warehouses or a SQL. Didn't make that picture go away. ETL stands for extract, transform, and load. The raw data is retrieved and transformed before being saved. The extract, transform, and load steps can be performed as a continuous pipeline of operations, suitable for systems that only require simple models with little dependency between them. An alternative to extract, transform, and load is extract, load, and transform. The process is different as the data is stored before being transformed. The data processing engine can take an iterative approach, retrieving and processing the data from storage before writing the transformed data and models back to storage. ELT is more suitable for constructing complex models that depend on multiple items in the database through things like periodic batch processing. Here's a simple table with the advantages of the two in most cases. Another generalized approach that exists, of course, is the Azure Data Factory, the cloud-based data integration that lets you create data-driven workflows for all this kind of stuff. For our data analyst, there are tons of ways that you can visualize data, from bars and columns to line charts and matrices to key influencers and tree maps to scatter plots and dot plots, and even a geographic map, if you have geographic data, of course. So again, data analytics is concerned with examining, transforming, and arranging data so that you can study it and extract useful information. Great when meeting with managers and C-suites. These tasks not only include analysis, but also data collection, organization, storage, and all the tools and techniques used. You have the descriptive and analytics. They help answer questions about what happened based on historical data. You have the diagnostic, which helps answer questions as to why things happened, like identifying anomalies, collecting data, and using statistical techniques to find relationships. There's also the predictive. Answer questions about what will happen in the future, like trends that for something that might reoccur, like an attack. You also have cognitive, to draw inferences from existing data and patterns, derive conclusions based on existing knowledge bases, and then add these findings back into the knowledge base for further inferences. A self-learning feedback loop. There's also one more that I forgot to add here, is the prescriptive, that helps answer questions about what action should be taken to achieve a goal or a target. All these ways we can use data to answer questions, to predict the future, to look at the past, to be able to graph all these things and answer all those kinds of questions for businesses. So as always, run through the pages of the learning path. There are no exercises in this entire section, this entire part. So you should be able to just knock out the knowledge check. And once you've done them all, you'll have all the XP, which is 3,600 for this part, and you'll be all good to go for next week. Any questions?
All good.
Awesome. Then I'll stop the live share and the recording.